In this video, we're going to actually start applying Newton's second law to working problems. Let's jump right in. Okay, we have example 1. Two forces, a 90 Newton and a 100 Newton force, act on a 1 kilogram object as shown. So we have a 100 Newton force acting in the x-hat direction, and we have a 90 Newton force acting in the y-hat direction, and they're acting on this 1 kilogram block. Now, I think you would probably guess that this block is going to start moving in this direction diagonally out, and we don't know the angle yet, and we don't know how fast it's going. That's what the problem's asking to determine. We want to find the acceleration. And so we're going to use the sum of the forces equals to ma. That's Newton's second law. So if I look at my sum of the forces, I've got two forces. I've got a 100 Newton force in the x-hat direction, and I have a 90 Newton force in the y-hat direction, and I'm just going to add them up, and that will give me the total force, the net force. Now, I know from Newton's second law that the acceleration is going to be the net force divided by the mass. And so I can take this 100 newtons x-hat plus 90 newtons y-hat, divide it by 1 kilogram. Newtons divided by kilograms gives me meters per second squared. And so I'm left with the acceleration being 100 x-hat plus 90 y-hat meters over second squared. Now, that is the acceleration. It's got an x component and a y component. Now, in terms of finding the magnitude of the acceleration, I know that I basically have the x component and the y component like this. They're going to make a triangle, and I can use the Pythagorean theorem. So I'll have this 100 squared plus 90 squared is equal to this thing squared. I take the square root, and that's what I've done here. And that gives me 1.3 times 10 squared meters per second squared, or about 130 meters per second squared. Now, if I need the angle, we know that that's going to be the arctangent of the opposite side, which is going to be this 90 newtons, divided by the adjacent side, which is 100 newtons. Obviously, the newtons are on top and bottom are going to cancel out. And if I take the arctangent of this, I find 42 degrees. And so that gives me an acceleration of 130 meters per second squared, or 1.3 times 10 squared in scientific notation. My angle theta is going to be 42 degrees. And that's going to be the acceleration of that guy there. Example 2 is to determine the force of gravity acting on some object that has a mass m. Now, the force of gravity, that's another way of saying the weight. And so I just want to make sure that we know that that's what we're talking about here. The weight of an object is the amount of force that gravity is pulling it down into the earth with. And so, but in order to define that, we're going to just say the sum of the forces is equal to m times g in the minus y-hat direction, or simply mg downwards. And of course, we know that little g is the acceleration due to gravity. It's not gravity. Gravity is the force. That's this guy. That's the force of gravity. Little g is not gravity. It's the acceleration due to gravity, 9.81 meters per second squared. And it's in the negative y-hat direction. And so the weight, we can simply say that the weight is equal to mg, and that is the force of gravity. And of course, we know that it's going to be pointing downwards. Now let's talk about weight just a little bit. There are a few points that are worth noting and remembering. So first of all, we just saw the weight of an object can be determined by its mass times the acceleration due to gravity. That is, the weight is equal to m times little g. Now, what is weight? Weight is a force. That means it's typically going to have units of newtons or pounds. There are some other force units that you may encounter, but these are definitely the main two. And we also want to note that weight and mass are related. How are they related? Well, we know that W is equal to m times little g. So they're related by the acceleration due to gravity. But it's very important to understand that mass and weight are different things. If you go to the moon, the force of gravity pulling you into the moon is less than the force of gravity on the Earth. So your weight on the moon is different, but your mass is going to be the same. Unless you go and you chop your arm off or something, you're going to have the same mass on the moon as you have on the Earth. But your weight is going to be different because the gravity is different. Weight is the force of gravity. The next example that we want to look at, example 3, is calculating the normal force. And so what we have here is we have a block that's sitting on a table, and of course we know that that block is going to be pushed into the table with a weight that's equal to m times little g. The table is going to push back with a force. We know that because it's not accelerating. It's sitting there, it's balanced, and so the net force on this block, if it's not accelerating, has to be 0. So there has to be some other force pushing it back, and we know that these forces must balance. We also know this from Newton's third law. The weight is pushing the block into the table has to push back. That's what Newton's third law tells us. And so the force that the table pushes back with, we call that the normal force. And it doesn't have to be a table. Obviously, this could be the floor, and I could have a block that is being pushed into a wall, and then that wall would push back with a normal force. And the thing about the normal force, that's a funny name. Why is it called the normal force? I mean, is there an abnormal force? No, it's not that kind of normal. In mathematics, very often the word normal is used to indicate that something is perpendicular. It's just a fancy way of saying perpendicular. And so it's called the normal force to remind us that this force is always going to be perpendicular. How do I know that? Because if the weight pushes this block into the table, there's no force making this block accelerate side to side. The normal force is back against the force that's pushing it into the surface. It's not side to side. And so that normal force is always 100% going to be perpendicular to the surface. Even if the surface is curved, you will still find at the point where the normal force is being applied, it's perpendicular. And actually, it would be perpendicular to the tangent line that intersects the curved surface, or the tangent plane that intersects that curved surface at that point. But the normal force is always perpendicular to the surface, and that's why it's called the normal force. So now we know what the normal force is. How do we calculate it? Well, we're going to use Newton's second law. I have this block that's sitting on a table. It's got two forces on it. It has the normal force and it has the weight. Now I've got my coordinate system here to tell me which directions are positive and which are negative. So I can see the normal force is in the positive y direction and the weight is in the negative y direction. Now I could technically have called this the sum of the forces in the y direction, but there are literally no forces at all in the x direction here, so I'm just ignoring the x direction. So we can say the sum of the forces is going to be positive normal force plus negative weight, so that's Fn minus mg, and that's, of course, the sum of the forces is equal to the mass times the acceleration. But this guy, it's not only not accelerating, it's not even moving, so we know the acceleration must be 0, and so I can cancel out ma, because anything times 0 is 0, that whole term goes away, and so I can say the normal force minus the weight is equal to 0. I bring the weight over, I solve for the normal force, and I find that the normal force is equal to the weight. Now I want to take a moment to comment about this, because you're going to find there are a lot of problems for which this is true, specifically that the normal force is equal to the weight. But we're also going to see lots of situations where the normal force is equal to something different than the weight. And so how do you figure out whether or not the normal force is equal to the weight or whether it's equal to something else? Well, I've already showed you. When you want to find the normal force, you do the sum of the forces. Now this normal force, if it were a wall, you'd have the normal force pointing out horizontally rather than vertically. But whichever way the normal force is pointing, you do the sum of the forces along that direction, and you can just say the sum of the forces equals to ma, and then you solve for that normal force. And that's the way you find what the normal force is. My students sometimes get into the bad habit of seeing many problems where the normal force equals the weight, and then they get to a point where they just see a problem, they go, oh, normal force, that equals the weight, and they start plugging it in. You can't do that because the normal force might not be equal to the weight, it might be equal to something else. You have to solve for the normal force. And if you get any one thing from this video, that's probably the most important thing in this whole video, is the idea that you have to solve for the normal force by doing this sum. The sum of the forces equals ma. So we can actually look at some examples where the normal force is not equal to the weight. And here's a case where that will be true if you simply add an extra force in the vertical direction. So I have this force here. It's an extra pushing force pushing the block into the table. Maybe someone is sitting on the block and their weight is pushing on the table. Maybe they stuck their hand there and they're just pushing it down. It doesn't matter what it is, but there's some force pushing this block into the table. And of course, the block still has its weight. If this is the case, can we figure out what the normal force is? Now, this case is simple enough, you could probably guess it, but let's go ahead and do what we're supposed to do. Let's do the sum of the forces. Notice how I said you're supposed to do that? I want to see that. If you're taking a class from me, I want to see you doing these sums, showing me where you're coming up. Don't just write down the answer. Show me that you understand where it comes from. So anyway, we've got the sum of the forces, and again, this is in the y direction. We have the normal force, which is in the positive direction, minus the weight, because it's pointing down, minus the pushing force F, because it's also pushing down. And so when I solve for the normal force, I bring these two guys over to the other side because ma is equal to 0. The normal force minus the weight minus the pushing force are equal to 0. I solve for the normal force and I get it's the weight plus the pushing force. Now I think that would make sense to you because you know that the normal force is the force that the table has to push back with. So the weight is pushing the block into the table. The pushing force is pushing the block into the table. How much does the table have to push back with? It's got to push back with the sum of those two forces. And this is what Newton's second law tells us. So we can see clearly that the normal force is not just the weight here. It's the weight plus this additional force. Now this is a similar example, except instead of a pushing force pushing the block into the tabletop, we have this force pulling the block upward. Now, there is a caveat here. I want to make sure that this force is not bigger than the weight. What happens if this force is bigger than the weight? Then this block is going to start accelerating upwards. And guess what happens to the normal force when the block loses contact with the table? I hope you guessed that it goes to 0, because it does. There has to be contact between the block and the table for the table to exert a normal force against it. But if this block is less than the weight, the block is not going to accelerate upward. It's not going to move upward, but the weight is being counteracted by this, and so the normal force is not going to be equal to the weight. Think of it like this. If a heavy block was sitting on your foot and crushing your foot, somebody might come by and try to lift it off of your foot to help you. They may not be strong enough to lift the entire block off of your foot, but they could maybe provide enough force upwards to keep the weight from crushing your bones. And then maybe someone else could come along and help them. This is the idea. This force is going to effectively reduce the amount of force pushing the block into the table, so the table's not going to have to push back as hard. But we want to be able to see this with math, because math makes it real. And so if, again, I do my sum of the forces, I'm going to have the normal force, which is in the positive direction, minus the weight. We see the weight is in the negative direction. But now my pulling force is also in the positive direction, so it's going to be plus positive. And so I've got the normal force minus the weight plus the pulling force is equal to ma. And of course, as it has been in all of these examples, acceleration is 0. And we can solve for this. The mg comes over and becomes positive. The force comes over and becomes negative. And so we solve for the normal force and we get that it is the weight mg minus the pulling force F. And just like we said, the normal force is reduced by this pulling force. If this guy weren't here, the normal force would be the weight. But because this force is pulling upwards, the effective normal force is reduced because you're subtracting. Let's look at another example with normal forces. Here I have a block that is on the floor pressed up against the wall, and it's being pushed into the wall with this force that is at a downward angle theta. Now let's think about this downward force for a moment. It's going to have components in the x and y directions. So here we see I've drawn in the x component of the force, and I can also draw in the y component of the force, which would be pointing downward. So we have the x and the y components. And so this x component of this downward force is going to be pushing the block into the wall, and the wall is going to have to push back with its own normal force. And so I've labeled that force as F sub NW. That's the normal force with the wall. Now the weight is pushing the block into the floor, and this downward force also has a vertical component that is pushing the block into the floor. And so we can solve for each of these normal forces simply by doing the sum of the forces in both the x direction, which will give us the normal force with the wall, and the sum of the forces in the y direction, which will give us the normal force with the floor. Now this is a great example to show you a nice technique that physicists often use to analyze these kinds of force problems. It's called the free body diagram. And what you do is you take all the forces in your picture and you connect them on a coordinate system so that they have a common origin. And remember, we have a rule about vectors. We can scoot them anywhere on the page that we want as long as we keep the length of the vector and the direction of the vector the same. So I've taken this vector here and I've scooted it there so that it starts from the origin. I've taken this vector here, I've scooted it over here so it starts from that same origin. All of these vectors start from the same origin. Now, this one force F, the downward pushing force, is at an angle with the x-axis, so I want to break that into x and y components because I want all my forces in my free body diagram to be represented in terms of their x and y components. And technically, I probably should have taken this guy here and scooted it over so that it had a common origin. I could have done it parallelogram style, but we'll let that slide. I think you get the basic idea of how free body diagrams are drawn. And so what you can see is that I've got this picture here with all these forces on it, and now I've organized all my forces so that it's easy to do the sum of the forces in the x direction and the sum of the forces in the y direction. And so this is how a free body diagram works. Now let me mention this for a minute because you'll see that I occasionally use these when I'm working problems, but not actually that often. I don't find that I need them very often. I don't find that they're very often helpful to me personally. There are physics professors that demand that their students draw a free body diagram for every problem involving forces. They want their students to always draw the free body diagram. That's how important they think it is. And I disagree. I think this is a very useful tool. I think it's useful because I use it. I use it whenever the picture gets really complicated. That's when I'm like, okay, maybe it's time for me to pull out my free body diagram and let me see what's going on with this picture a little bit more clearly. But if I don't need to use it, if the picture's already simple enough, why would I do the busy work of drawing it if I don't need it, if it's not going to help me? So I'm going to use it when it's helpful to me, but I wanted to for sure show you how to do it in case you might take Physics 2 from someone that's not me and they may want you to draw these dadgum things all the time, so you should at least know how to do it. But what I want you guys to do is I want you to play around with it. When you're working homework problems, when you're doing examples, pick a few problems and just try it. Just like just to make sure that you know how to do it, but also to kind of get a sense of whether or not it helps you. Because the reason so many physics professors make all their students do it is because there are a lot of students for whom doing this always helps them. It just like it organizes things in a way that clicks for them, and it's super, super helpful for them. There are other people like me who find it occasionally helpful, but often not very helpful. I don't know which you are. The only way, and you don't know either yet because you're new to this, the only way for you to know whether this is going to be helpful to you or not is to try it. And, play around with it, try it on a few problems and see if you like it, see if it helps you. If it does, use it. If it doesn't, don't use it. But if you're like me and you're not inclined to use it very often, at least be aware that it is a tool that you have in your toolbox. Don't let it get rusted. Bring it out occasionally when it's helpful. Because sometimes if you're looking at a picture and you're like, man, there's a lot of forces on this picture, that might be a time to think about pulling it out, dusting it off, and using it. Okay, so let's actually work this problem now. We have our free body diagram. We have all these forces. We are given that the mass of the object is 10 kilograms, so we can very quickly figure out what the weight is. We have mg is going to be 10 kilograms times 9.81 meters per second squared. That is little g, the acceleration due to gravity. And it works out to be 98.1 newtons. So we know immediately there is a 98.1 Newton force pushing this guy into the floor caused by its weight. Now this Brown force F, we can break into its X and Y components. We know that we're given in the problem that it is a 100 Newton force at a 30-degree downward angle. And so we know that the Y component is going to be 100 newtons times the sine of 30. Y sine of 30? We're told this angle theta is 30 degrees. The y component is the opposite side to the angle in this right triangle, so that goes with the sine. And so we can say this is 50 newtons downward. That is the y component of that force, 50 newtons downward. Now, I could have very easily put minus 50 newtons in the y-hat direction or 50 newtons in the minus y-hat direction, and that would have given me the direction, and that would have been perfectly fine. But I, for whatever reason, decided just to note that my direction is downward. And for me, that's sufficient. But it's important that you have both. When you're dealing with vectors, you always want to pay attention to both the magnitude and the direction because you need both for the full vector. Now, this is the y component. The x component is going to go with the cosine because it's the adjacent side to this right triangle. And so I can say the x component is 100 newtons times the cosine of 30, and that works out to be 86.6 newtons. And again, I've noted the direction to the right. I could have called it positive x hat. Whatever you want to do, it works fine. But now I have all of these forces. I have the weight, I have my pushing force, which I've broken into x and y components, and now I can solve for my two unknown forces, these two normal forces. So let's look at finding the sum of the forces in the x direction. There's actually only two. There is this f of x, which is f cosine of theta, and then there is the normal force with the wall pushing in the opposite direction. And so if I do the sum of the forces in the x direction, that's going to be fx, that's this pushing force in the x direction, minus the normal force with the wall. It's equal to ma. The sum of the forces is always equal to ma, but this guy is equal to 0 because this block is not only not accelerating, it's not even moving, so for sure it's not accelerating. And so when we plug in, and of course we know this is going to be the 100 newtons times the cosine of 30 degrees, and that works out to be 86.6 newtons. That is the force that is pushing the block into the wall, and that is also the force of the wall pushing back. So we've done the sum of the forces in the x direction up here, and I'll just make that explicit there. The sum of the forces in the x direction give us that the normal force with the wall is equal to 86.6 newtons. We can also do the sum of the forces in the y direction, so we can say the sum of the forces in the y direction, and that's going to be the normal force with the floor minus the weight minus the downward component of this force, F sine of theta, and that was at 50 newtons in the downward direction. So that's going to be the sum of the forces in the y direction is going to give us the normal force with the floor, and then that's going to be minus mg, and then minus the y component of that pushing force, Fy. And of course we know that that's equal to ma, which is again going to be equal to 0. Now we can bring these two guys over. We can also just go ahead and plug in the numbers because we have them. So we can say that the normal force with the floor is going to be equal to mg, which we found previously to be 98.1 newtons, plus the downward pushing force, which we found to be 50 newtons. And so we can say that the normal force with the floor works out to be 148.1 newtons. And so we have the normal force with the floor. We also have the normal force with the wall up here. And that's what the problem asks us to find. This next example might look a little scary, but it's actually not as bad as it looks. Let's look at what we've got here. So the problem says we've got two 10-kilogram masses are connected by an ideal rope. That is, a rope that has negligible mass and that doesn't stretch. The fact that we're saying that it has negligible mass, that is an assumption that we make that tells us that the tension is going to be uniformly transmitted through the entire rope. Whatever the tension is on this side, it's going to be the same tension on the other side, in the middle, all across the rope. And the fact that it doesn't stretch means that as this system accelerates, they're going to accelerate together. The two blocks are not going to get further apart. It's not a rubber band. They're all going to move as one unit. This could be a rope. This could be like a thin metal bar that's fixed, that's attached to these blocks together. It doesn't matter. The whole point of the doesn't stretch is that these guys are moving together as one unit. And we're also given that there is a 100 Newton force pulling on these blocks, pulling the system together to the right. And that's going to cause them to accelerate in the x direction. And we're also told to assume that there's no friction in this system. And this is really our approach for many things in this course. We like to make a lot of simplifying assumptions, like the idea that there's no friction. And then these assumptions, the mass is negligible, all these things, they make the problem simpler than it would be in the real world, so that we can learn how to solve these kinds of problems. And then we say, okay, how do we handle friction? How do we handle a rope that stretches? How do we handle a rope that has mass? And we can put these complications back in later once we've built this foundation. So we're making this a little bit simpler so that we can get there. In any case, I have the actual problem sort of boxed over here in green. We're asked to find the acceleration of this system. That is, I've got a net force here. There's no friction. This guy's going to be accelerating to the right. And then I want to find that acceleration. And then I want to find the forces acting on the two blocks from the rope. This force F21 and F12. And again, this is the force of block 2 acting on block 1. So this is my notation, F21 for block 2 on 1. And you have to be careful with that because there are lots of people that do that backwards. They would say F21 would be 1 on 2. I say F21 is 2 on 1. You need to know what your label means. You need to be very careful about your labels and then be consistent with them. Actually, a few minutes ago, I told you that the business about solving for the normal force was the most important thing in this video. I lied. This is the most important thing in this video. Using labels. You need to look at how much stuff is in this problem. And I've got two different blocks. I've got all kinds of different forces in it. I need to be very careful about how I label them. So look at what I have here. I've got M sub 1 times G. That is the weight of block 1. And that's usually how you would say that M sub 1G. A lot of people, though, they get lazy and they just say M1G. And I like to be lazy when it's helpful, so I'm going to just say M1G. This guy would be M2G. That's the weight of block 2. What do you think Fn1 was? It's the normal force. We don't know that these two normal forces are the same. It turns out in this problem they would be, but they don't have to be the same. And so we're careful about our labels. This is the normal force acting on block 1. This is the normal force acting on block 2. This is the force of block 2 acting on block 1. That's the rope pulling it. This is the force of block 1 acting on block 2. That's the rope pulling back. Now, this 100 Newton force, we have to be careful about that. This is only acting on block 2. You could imagine there's another rope here and we're pulling on this rope. This force is not pulling on block 1. Only F21 is pulling on block 1. This guy's pulling on block 2. And so we want to be very careful when we draw our picture to make sure that our forces are acting at the right spots. So again, we want to find the acceleration of the system and we want to find the force acting on each mass. And I'm going to show you a couple of different ways to approach this problem, but one thing that you can do to make your life easier, when you have multiple masses in a system, you can isolate the forces on each individual mass. And that's a very useful thing to do in a lot of circumstances. So let's try that first. We're going to take each of these two masses and we're going to look at just the forces on that block. Now let's look at block 1. I've got my weight, of course, M1G. I've got my normal force in Fn1. But these are all in the y direction and they don't matter because this thing is not moving at all in the y direction. And so the only force that matters for determining how it's going to move is this F21. And so we're going to look at that, and that is the only force creating an acceleration on block 1. Now let's look at the other block, block 2. Again, we have the normal force and the weight. They're going to cancel. They're going to not affect the motion of the block. But if I consider block 2, I'm looking just at block 2 here. I've got these two green guys, we just said they cancel, but then I've got my 100 Newton force pulling it to the right, and I have my tension force. This is the force of the rope, or actually the force of block 1 pulling on block 2. And so this is my F of 1 on 2, and these are the forces in the x direction, so those are the ones that are going to contribute to the acceleration. If there were no rope, you would have just 100 newtons equals to M2A, and you could solve for the A. But because the rope is here, that rope is dragging the block, it's opposing this force, and so that's going to actually reduce the acceleration. Okay, let's apply this. So we have for block 1 here, I've drawn block 1 again, and I know the only force in the horizontal direction is that F of 2 on 1, and I've drawn my little coordinate system here to show me my positive direction. And so I can do for block 1, for mass 1, I can say the sum of the forces in the x direction are just this F21, and that's equal to M1A. And again, notice it's not the sum of the forces is equal to MA. My labels have to be careful. It's the sum of the forces in the x direction are equal to M1A, because we're only talking about block 1 here. Now I've drawn block 2 here, and we know there's two forces on block 2. My coordinate system is still the same. I have the force that's pulling the two blocks, and then I have the force of the rope pulling back, F12, that's 1 on 2. And so if I do the sum of the forces in the x direction, I get F, which is in the positive direction, minus F12 because it's pointing in the negative direction, and that's equal to M2A. And so we have for block 1, F21 equals to M1A, and for block 2, mass 2, we have F minus F12 equals to M2A. And that actually gives us three things that we don't know. We've got F21 that we don't know, we've got F12 that we don't know, and we know the acceleration that we don't know. The only thing we actually know at this point are the masses. Actually, we do know one other thing. We know that these two guys, they have to be equal in magnitude because they are Newton's third law action-reaction forces. Block 1 is pulling on 2. Block 2 has to pull back on 1 with an equal and opposite force. And so their magnitudes have to be equal. And so what I can do is I can just say F12 is equal to F21. And what's F21 equal to? It's equal to M1A. So I can take this M1A and I can substitute it in down here. I can just take this guy and substitute it in there. And I get that F minus M1A is equal to M2A. There's M2A. That guy there is M1A. I just plugged it in. And now I can solve for F. Okay, now we want to solve for F. What I had previously was that F minus M1A is equal to M2A. And I can take this M1A and bring it over there. I get M1A plus M2A. And then I can obviously factor out the A. And I get that the force is equal to M1 plus M2 times A. In the problem, each of the masses were given to be 10 kilograms. So we know that 10 plus 10 gives us 20. If I divide 100 by 20, I get that the acceleration is equal to 5 meters per second squared. And that's the acceleration of the entire system. Now let's look at all of these forces in the x direction again. And of course I have my normal coordinate system, x and y, showing me directions. Now, if I look at this guy, I can see that these two forces, the forces of tension and the rope, those are like Newton's third law kinds of forces. They're going to cancel. And so I could treat, rather than isolating these blocks, I could treat these as one system moving all together. And so these guys are going to cancel out, and I could just simply say the sum of the forces acting on this system is just going to be F. You could say F plus that one minus that one, and then these guys cancel. But really, just looking at the picture, you could say this guy is F, and that's the only force moving the whole system together. And then the mass is going to be the total mass, M1 plus M2. Look what I have here. This is what I would get if I started out looking at the entire picture instead of isolating the masses. And so this is another way to do that. Why the heck did I show you all that complicated isolating the masses stuff then? Well, the reason is because the problem also asked you to find the F21 and the F12. If I just have this, then that doesn't let me do that. But if the problem were just simply find the acceleration, I would not isolate the masses. That just makes it more complicated. I'd just go straight to this guy. I can see it in the picture. If I just want to find the acceleration, I've got F equals ma. Boom. That's the total mass. That's the total force. I can solve for A. Now, because I did see in the problem that I also wanted these individual forces, I did isolate the masses because that lets me solve for them. So how do I solve for them by isolating the masses? Well, let's look again. I've got my block 1 here. I've got my F21, and that's the only force in the x direction. F21 is equal to M1A. I just solved for A. I now know that the A is 50 meters per second squared, and so this force has to be 10 kilograms times 5 meters per second squared, and that's 50 newtons, and I can see from my picture, or from the fact that this is all positive, that this is going to be 50 newtons to the right. Now, what about F12? I could just by inspection go, oh, Newton's third law tells me it's got to be equal and opposite, so that means it's going to be 50 newtons to the left. And so now I've solved for the problem. I found the acceleration, and I found F21, and I found F12. Now, I want to point out that if I look at the forces acting just on block 2, again, I'm isolating block 2. In the horizontal direction, we've got 100 newtons to the right minus F12 to the left. I can set up my sum of the forces equals to M2A and solve for it. And so solving for F12, if I bring this guy over here and that guy over there, and I'll find that F12 is equal to F minus M2A. Just solving this for F12. And so that's 100 newtons minus 10 kilograms times 5 meters per second squared. Again, that gives me 50 newtons, and we can see in our picture that it is going to be to the left. And that's our answer. It works either way. I can use Newton's third law, or I can solve it directly. And by the way, on a test, don't just write down the answer. You need to show me that you understand where you got the answer. Now, if you do the math, it's obvious where you got the answer. But, if you see that you can say, oh, this has to be true by Newton's third law, you could skip doing all of this math and just say, oh, block 1, I found that F21 was 50 newtons. F12 has to be the same magnitude in the opposite direction just because of Newton's third law. Okay, so we're going to move on and we'll do some additional examples in the next video. We're going to do a lot of different examples because there are a lot of different ways that this simple equation, F equals ma, it can be applied in so many ways. And so we're going to try to show you a lot of different ideas about how we can use this equation to solve problems and understand how things work in our universe. It's really kind of cool how many different ways it can be used.